A2 Maths, locating roots. Okay, so what I'd like you to do, something simple to start with, just have a go at filling out that table of values for me, please. Take your x values, substitute into that cubic function, and just write out the answers for me. Okay, pause if you need to. Let's see what solutions you got then. So you stuck -2 in, and you got -10, you stuck -1 into it, and hopefully you got 1, and so on for those values. Now that you've got those values, what I'd like you to do is have a think about this question then. Between which integer values of x, so your integer values are your 1, 2, 0, -1, -2, between which of those integer values do you get the solutions to this cubic equation? Okay, now it's not a whole number answer, but I'm not looking for a solution. All I'm looking for is between which x values the solutions will lie. Okay, so have a think about that. Pause if you want some more thinking time. Right, now you'll be correct in thinking that the solutions to that equation will be somewhere between, let's say, -2 and -1. There is definitely a solution between those two. You should be thinking, why is there definitely a solution between those two? And the reason why there's definitely a solution between those two is when you subbed in -2, you got -10. When you subbed in -1, you got a positive answer 1. Somewhere between -10 and 1, you had this change of sign. It was negative to start with, and then it became positive. And if it's negative and it became positive, somewhere in between there, certainly for a cubic function like this, somewhere between there should have been a 0. So that means that somewhere between -2 and -1 should have been a 0. The same idea happens here. +1 to -2, you can't get from 1 to -2 without crossing through 0. So therefore there should also be a root between there. These two, -2 to -1, are both negative. You cannot say anything when they're both the same sign. Okay? But then from -1 to 22, that's okay. There is definitely a change, so therefore there should be a root. And that idea of noting a change in sign is the key thing to knowing where there's a root in between. If there is a change of sign from positive to negative, there is a root between them. There is a solution. Okay? And that is the important bit that you need to get down in your notebooks under locating roots. The examiner's looking for that. Change in sign means root or a solution between them. So there's an example on the board. So we've drawn our graph and we noticed that if we get a positive answer out, and if another root gets a negative answer out, there's no way to get from that negative to that positive without passing through 0. It's just not possible to change from positive to negative without crossing 0 for a continuous function. I'll come back to that idea of a continuous function in a minute. Okay, so in this case, it has roots between -2 and -1, which we talked about, -1 and 0, but also 1 and 2. Okay, right, pause if you need to take any notes down. Right, so grab this down in your notebook as well, and you might want to just pause it and have a think of it yourself. So pause, copy it down, we'll look through the solution. Okay, so let's have a look at the solution then. So to show that this equation has a solution between 1 and 2, not the answer to it, just has a solution between 1 and 2, what I need to do is I need to show that either 1 is positive and 2 is negative, or 1 is negative and 2 is positive. I need to show there's a change in the signs between these two. So when x equals 1, I substitute it in, substitute 1 in, and I get -1.282. That's fine. There's nothing wrong with being negative. If the other one's a negative, I can't say anything at all. But if the other one is positive, I'm going to substitute 2 in, lo and behold, the other one's positive. So therefore, change in sign, make with the language, there's a change in sign between x equals 1 and x equals 2. So therefore, that value must cross the x-axis. So therefore there is a solution between x equals 1 and x equals 2. Okay, So on the same set of axes, I want you to sketch the graphs of y equals sine x and y equals ln x and show that the graphs intercept between 2 and 2.5. Okay, so you can show it on the sketch, but then we also want to show it numerically as well. So again, pause, sketch your own graphs. Don't wait for mine. Hopefully you can sketch both of those functions. You need to be able to sketch both of those functions without your notes. And then you can also think about the problem we're trying to show it. So you might want to just leave that bit till we go through it together. Okay, so your sketches first of all. Hopefully you know how to sketch sine. Ln is the one that might have stalled you. Remember that the ln function is the inverse of exponential. Exponential sort of goes across and comes up like this. It crosses at 1, it goes up like this. So you reflect that in the line y equals x. You get the same idea. It gets close to this line, it comes up, it crosses at 1 and does that. So your log graph will look like this. Noticing that that's pi, so that's about 3 there. That's why it's crossing about 1. It's certainly not a squared grid, this one. Okay, it's not to scale. But what's important is showing that it only has a single root, a single solution. What I need to do is show that solution is in between 2 and 2.5. It certainly looks about right, doesn't it? If that's 3.14, 2, 2.5, it looks like it's close. Let me make sure I can show it numerically. Now the problem is, unlike before, this equation is looking for when these two intercept. We're looking for where they cross. Now I can't use the trick I used a minute ago of showing a 0 because it doesn't equal 0. So the way we can do it is just rearranging this equation, taking this equation, rearranging it so that it's in the form some function equals 0, f of x equals 0. So if I do that and rearrange it like this, equaling 0, I can now check either side to check for a change in sign. Yes, you'd be right in thinking you can have sine x minus ln x equals 0. That works just as well. So what do I do then? I can now get my calculator. I can stick number 2 into both of these, remembering that I'm in radians, not degrees, in case your calculator gets an error or something wrong. So stick number 2 into it, stick 2.5 into it, and hopefully we get a change in sign. So let's have a look. When x equals 2, ln x sine x gets ln 2 sine 2, which is roughly minus 0.2162. When I stick 2.5 in, lo and behold, I get those two, ln of 2.5 sine of 2.5 equals positive 3.178. I can see they're continuous graphs, there's no issues there, so therefore there is a change in sign between x equals 2 and x equals 2.5, shows that these two intersect within that interval. Okay, they intercept each other. Previously we talked about where it intercepts the x-axis, which is still the intercept between two lines. Okay, even when it's crossing an axis. Okay, I would like you to have a think about these two answers and tell me what you can say about the roots. Okay, so I'm going to just allow you to pause, have a think about both those solutions. Okay, so this first one then, all right, if we look at the first one, is you would be well within your rights to think both of those are positive, therefore they have no roots. But have a look at the example underneath it. Okay, when I put 2 in, I get a positive 14. When I put 3 in, I get positive 8. Does that mean there's no solutions between it? No, not at all. In fact, this one has 2 solutions between those roots. The moment both of them are the same sign, you cannot say anything at all. You can't say there's no roots because there could be 2 roots, there could be 4 roots, there could be 20 roots in between those two numbers. You cannot say with confidence that just because both of them are positive means that they don't cross at all. Okay? Also, if you've got positive to a negative, I don't blame you for thinking there's definitely a root between them, but unfortunately that's not always true. And you've heard me use this word already. It's only true for continuous graphs. An example of a graph that's not continuous, let's go back to that, no roots, it has to have an even amount of roots. So in most cases, for this one, for example, 2 and minus 4 definitely got a root. No problem at all. All right. It's got at least one root. In fact, he went from 3 to 1. It's 1, 2, 3 roots. Okay. There's an odd amount of roots. But does that mean that you've definitely got at least one root? Well, not necessarily, and this is where you need to be careful. If the graph is something that is not continuous, and the graphs you've seen where it's not continuous would be something like the tan graph, okay, where the tan graph between certain values doesn't have solutions. The 1 over x graph is a graph that's not continuous. If you've got functions like that, there's an example of a 1 over graph. Now I could quite easily try two numbers in here. I could try the number 2 and get a positive answer out. I could try the number 4 and get a negative answer out. Does that mean it crosses? No. And the reason why it doesn't cross is because this graph is not continuous. So you need to be aware that some functions that have asymptotes, okay, in this case it has an asymptote just there, means that they do not necessarily fall into this change of sign definitely crosses rule. You need to be very wary of that. And the examiner will be looking for you to think about that when you think about change of sign means there's a root, not unless it's not continuous. Okay, if it's not continuous, that's not always true. Right, so what I'd like you to do is have a go at exercises 1.1 and 1.2 on those two pages and make sure you're considering whether graphs are continuous or not continuous when you think about using this technique.